So the next few pages here, we have some fragmentation patterns. Now, I'm going to leave these kind of open, and what we're going to do as we progress through our Chem 225 lecture is each chapter in our second semester course has a little section on spectroscopy. So it makes more sense to just cover these different types of fragmentation patterns as we are presented with the new functional groups. So we've already seen alkane fragmentation. So there's one bond cleavage, there's alpha cleavage, carbonyls, something called McLafferty rearrangement. You have loss of water for alcohols. So again, we'll go back and consult these as we are encountering these situations. So let's take a look at an example here together. Right, so here we have a molar mass of 86. So it's 86. Well, we already figured this one out on our previous example, right? We know that 86 was hexane essentially. So 6 carbons, just to review, a molar mass of 72. So that's a C6. So 86 minus 72 gives us 14. So H14. So does this mean that we have hexane? Not necessarily. We have to look at the fragmentation pattern there to help figure that out. And that's where the power of mass spec can really help come in. So it can tell us a lot about, for example, different isomers of the same molecular formula compound. So this molecule, let's look at what it is, and then we'll go through and we'll talk about some fragmentation patterns here. So this is actually 2-methylpentane. So it's an isomer of hexane. So let's take a look down below and let's look at least one of the fragmentation patterns that gives rise to perhaps one of the larger peaks that's on there. So if you look at the biggest peak here, it's at 43. Now let's talk about how we might get that. So I want to start off here by drawing this out as CH3, CH2. Put all our carbons in here. It'll help us keep track of what's going on as far as our cations and stuff. And so as this goes through, that electron beam, right, flies in and it kicks off a single electron, right? So we have a loss of an electron from this thing, right? So this is your M plus with a mass to charge equal to 86. But remember, next what happens is we have that fragmentation. So how might this fragment? Well, we've basically 86 and 43, right? We've cut this thing in half. 43 is half of 86. I don't know, I think a good place to think of cleaving this would be right here. Now when we cleave it there, what we want to do is we want to form the most stable cation. So where should we do that? Is it better to have a plus charge here or have a positive charge right there? Well, I'm going to go with this because that's going to give you a secondary carbocation. Right? So when we do that cleavage, we're going to get a CH3, CH2, and a CH2 down here, radical. Now that's not detected, remember? And then we're going to have our CH3, our CH, and our CH3 here with a plus there. That's detected. And that'll give you your mass to charge of 43 there. Okay? And so that's how you can look at the spectrum and guess, well, it must be 2-methyl pentane because that fragment is so abundant. Right? Other isomers of this won't result in that particular fragment. Well, let's take a look at an alkene. So we know that it's an alkene. Notice here that the parent molar mass is 84. So we're still going to go with C6. Right? 6 gives us 72. 84 minus 72 gives us 12. H12. Well, that works out, right? That is the molecular formula of an alkene or something that's cyclic. So I'll give you the structure, and then let's see if we can explain the fragmentation pattern there. So there's 6, and that's where our double bond is going to go on that, okay? So notice here we're at 55. Okay, so 55, well, 84 minus 55. So 55 actually is an M minus 29. You guys remember 29 is what we saw for that hexane, right? Remember when we lost the ethyl? An ethyl radical is 29 for its molar mass. So if we go through and look at what this is going to look like as far as our fragmentation is concerned, let's look. So here's a CH3. We're just going to draw this thing out. Double bond carbon here. You got your H down there. And then you have your CH2, CH2, CH3. Right? Plus radical. And remember, that is your radical cation with a molar mass of 84. And then this fragments, right? Remember that happens. So where do we want to do this? Well, we want to generate the most stable intermediate. So the best place to do this for this molecule is to recognize that that carbon right here actually is allylic. Remember, allylic means that we're adjacent to a pi bond. Right? So next to this pi bond. Okay, so then if we were to take that position and do a cleavage right there, well, let's look at what we get. You get a CH3, carbon, HH, CH2. Right? Here's another way of doing this, by the way. You just break the bond. So a CH2, CH3. So where is it better to put the plus charge? Here, because that's allylic. And then that would leave you with a radical right there. Right? And then here we can have resonance, right? So we go through, and our resonance structure would do that. Right? So that would give you CH3, carbon, carbon, CH2, H plus right there. So that's fairly stable. At least it helps stabilize the carbocation. And then that gives you a mass to charge equal to 55. And so that resonance is why that's the most abundant ion there. Now, one thing that happens with alcohols is that we typically see a rapid loss of water. And water has a molar mass equal to 18. So we typically see an M minus 18 peak present here, often with no M plus peak. So you see the M plus peak is basically empty right here, and the 70 is your M minus 18. So let's talk about how these two peaks are actually made. So with that structure here, we have a CH3, CH3, CH2, CH2, OH. Right, it goes through, and that becomes your molecular ion. But then very quickly, we have a loss of water here. And when we lose the water, the OH is lost, and one of these H atoms is lost here. So we get one H atom lost right there. So what you form here is CH3, CH, CH3, CH, double bond, CH2. Right? And then that's your new molecular ion, and then you kick off H2O. So this has an M to Z equal to 70. So that's why that peak is fairly abundant. It's kind of like your fake molecular ion. This can undergo fragmentation, and the best place to do that is right here. So when we do that, we have a CH3, CH plus, CH, CH2, right? And then that's plus CH3 radical, and then you of course have loss of water there also. So this mass to charge for that is equal to 55. Notice that it's the parent, which is, right, this number here. So 88 minus 15, that's your methyl, minus 18, right?